Okay, so let us continue our group theory problems with this next one, the 19th one. Now here, just like the previous one, the 18th one, we are given a group for which we have to find the permutation representation. And our group is now a 4-order group where these relations are true. That is, the squares of these two elements a and b equal e, and a and b commute with each other. So let's see the solution. So because this is just simply a matter of finding those functions tau g, because they are after all going to give us the permutation representation. So I am just simply going to write what we find when we try to calculate these functions. So in a of g, which is isomorphic to S4, we have tau e equal to e, then tau a is this permutation. It's a product of two transpositions, and these transpositions are, one of them is e comma a and the other is b comma ap. Then tau b is again another one such e comma b times a comma ab, and then we have tau ab also, and this one is eab a comma b. Yes. With this, the permutation representation of G is this function, this map psi from G into A of G, which is isomorphic to S4, such that psi sends the group element G to the function tau g, which is a bijection and is an element here, and that is the solution. Okay, now let us see once again, because we have already gone through one such solution to the previous exercise, but still let us see for this one, let us recall what is it that we have done. And in order to understand what we have done, and again to see once more what a permutation representation is, let us recall the proof of Cayley's theorem. What does Cayley's theorem say? It claims that any group G whatsoever can be found inside a permutation group as a subgroup. That means inside A of S for some non-empty set S, and in the proof of Cayley's theorem we choose that S to be G itself. And in proving Cayley's theorem, how we proceed? For any arbitrary element, group element G, we define a function tau suffix G, which is a function from G to itself, and its definition is this: a group element H coming from capital G, of course, on it if you apply tau g, then it's just multiplying h by g from the right side or forming the product hg. One can then prove, and in fact we have already done so, that this tau g is a bijection on g, and as such tau g itself is an element in this permutation group ag. And then what we do, we then consider this map psi from g into a of g, which maps the group element g onto tau e, and one finds that this psi is a group homomorphism which is 1 to 1. That means it's an isomorphism, and that is why the image of g in this group A of g under this map is the copy of g, that is isomorphic to g and is a subgroup of this permutation group A of g. This way, this map psi helps us represent the group G inside this permutation group A of G, and under this representation every group element G is thought of as this permutation tau G. And because of the choice of the set that we have made in proving Cayley's theorem, that is taking G itself, we end up having permutations of the group elements themselves, and that's what we see here. So if we try to see what went on here in this specific case for this specific group, let us try to see what actually, how are we getting these maps tau G for each group element. So tau E means what? Tau E would do what? It would multiply, when you apply tau E to a group element G, you are going to multiply G by E from right side, which actually is going to change nothing. It will keep G itself, because G E is G. So tau G does not change any group element. That is true in general for any group. It is true for this particular group also. In other words, tau G is the identity permutation. That is why we write tau E is equal to E. Tau E is the identity permutation. You should look carefully that this E that you see in the suffix is the identity element you have here in the given group, whereas the E that you see on the right side, that is the identity permutation on these four symbols, which maps E to E, A to A, B to B and AB to AB. That means it does not change any symbol. How would you calculate tau A? Tau A means multiplying every group element from the right side by A. So if you apply tau A on E, on this symbol E, that means EA. EA is A, so E goes to A. And on A, if you multiply tau A, that means AA. AA is A square is E, so you come back to E. So that's how you get this 2 cycle. Okay. Then when you multiply B from the right side by A, that is you apply tau A on B, you get BA, but BA is AB, so that's why B goes to AB. Then on AB, if you multiply tau A, then you have ABA, but A and B commute, so the ABA is A square B, but A square vanishes because it's identity, so you have B, that's why AB goes back to B. And so the permutation that tau A is of these 4 symbols is this particular permutation, which is the product of these 2 cycles. And similarly you have tau B and tau AB. And this map, which gives you the actual way of getting the isomorphic copy of G inside this permutation group, is called permutation representation, because it is allowing you to represent every group element as a permutation. every group element G has a permutation tau G. And A of G is isomorphic to S4 because this is the group of permutations of the symbols in G, because there are 4 symbols, so it's just S4. Okay, so that's how the thing goes. So moving on, let's now see the next one. In this case, the given group is S3 itself. Let G be the group. Find the permutation representation of G, and there is a small note also. Just like in the general case, psi maps G into A of G in a one-to-one manner and it's a homomorphism. Here S3 will be mapped into S6 because we are going to consider A of S3 and S3 itself has 6 elements, so we are going to consider all permutations of 6 symbols, so S6. So that's why the note is this. This gives an isomorphism of S3 into S6. And let me also remind you of one more thing. In this text, isomorphism means one-to-one homomorphism and that's it, not onto. But in some other texts, isomorphism means bijective homomorphism. Here, however, if you want to say that a homomorphism is an isomorphism is onto, you have to explicitly mention it. Okay, let's see this one. Okay, now before I write this solution, there is something to be said about the notation that we are going to use. Normally, when we talk about S3, now because we know about permutation groups in general, we know these notations, that is what we normally use. For example, this is an element in S3, 1, 2, a 2 cycle. What it really is that it is a permutation of the 3 symbols 1, 2 and 3. It maps 1 to 2, 2 to 1 and 3 to 3. However, when we were introduced to S3 for the first time, when examples of groups were presented to us for the first time in the beginning of group theory, that then we did not know about these notations. Then what we did, we used some names, phi and psi, for this type of functions. And in terms of phi and psi, if you recall, we introduced 2 specific functions, phi and psi. And phi, I think if I am remembering correctly, is this one, and psi is this 3 cycle, 1, 2, 3, which sends 1 to 2, 2 to 3 and 3 to 1. And then we expressed the other elements of S3 in terms of phi and psi. Like you may remember this thing. The identity element of course is there, e, then another element is this phi, then psi square, then phi psi and psi phi. Okay, so that way we get 6 permutations which are distinct, and they give us the entire list of all the elements in S3. Now why I am saying all these things now is because you can see that if I use this notation, which is actually the standard way of writing permutations in general, these things that were first introduced were just introduced at that time because we did not know about these general notations. We did not have the need to know them generally. We just wanted to present one example. So that's why such names were chosen. But now if I use this standard notation to write functions like this, for example, I want to calculate tau suffix 1 comma 2. Then inside, if you again use cycles like this, then it will be permutations of permutations. Actually it's going to be permutations of permutations, but if I use this notation, then it will look very clumsy. So instead I will use this phi sign notation. Okay, so this is how I am going to start the solution. We know that, so first I am going to write the elements in S3 in terms of those functions phi and psi. We know that S3 consists of the identity, the function phi squared, phi psi and psi phi. So you would need, in order to calculate with these functions, you would need to know what actually phi is, what psi is. So you have to go back to that example. Now I am just going to write the final result in A of S3, which is isomorphic to S6, because there are 6 symbols whose permutations we are considering in A of S3. These it would be better if I write like this, like an equation array. Tau E is of course equal to E. You do not even have to think about this. This is always going to be the case in no matter what the group is. But then next comes tau phi, and this one is this permutation E comma phi times phi psi comma psi squared times psi phi comma psi. Okay, next tau psi. Tau psi is a product of 2-3 cycles, and one of them is E comma psi squared, and the other one is phi psi comma psi phi. Next, tau psi square is also just like this one, a product of 2-3 cycles, but here the cycles are a little different. I mean the orders change. E comma psi square comes first and then psi. Here also these second and third entries switch places. Phi psi phi phi psi. So for that means 2 more, E phi psi. We will verify 1 or 2 of these things to see if what we are writing is just some random nonsense or actually it is what it is supposed to be. So the next one is tau phi psi E comma phi psi, then I should not make any mistake. Psi phi comma psi square, and finally tau psi phi, and this one is E psi phi phi comma psi square, and the remaining 2 phi psi comma psi. If you have a 2 cycle, then it does not really matter whether you write E first or psi phi first, because they are the same thing. Okay, so these are the functions, and with these we have our permutation representation of S3. Now as the note says, the representation is one isomorphism of S3 into S6, but not necessarily this is the only one. There are other isomorphisms of course also. I mean there may be. With this representation of S3 is, but note carefully, you cannot write psi here because that symbol has already been taken. So let me just for the sake of this one only denote the isomorphism by psi prime of S3 into A of S3, which is isomorphic to S6, and of course the rule for this function is this. That's it. Okay, let us now see, as I said, let's verify any 2 of this. So let's verify tau psi square, whether this is really what we get. Applying tau psi square on any one of these symbols means multiplying the symbol by psi square from the right side. So when we multiply E by psi square from the right side, that is E psi square is psi square, so E goes to psi square. Multiplying psi square by psi square gives us psi to the power 4, but we already know that psi cube is E, so psi to the power 4 is psi, and then multiplying psi by psi square gives us psi cube, which is E, so we come back to E. Next, phi. If you multiply phi by psi square, you get 5 psi square, which is equal to psi phi. You go back to that first example where S3 is introduced. There you will get these facts. We already verified these facts there, that 5 psi square is equal to psi phi. So that's why we get this. Okay, now let me do one of these. Let me show it here briefly. If I multiply this by psi square, what do I get? 5 psi square is psi phi, which means I get psi square phi, which in turn is equal to phi psi. So that's how we get phi psi from this one. And if you multiply phi psi by psi square from the right side, that is, if you do this, then you get 5 psi cube, but psi cube is e, so you get 5. So that's why this comes back to 5. And if you want, you can actually you should verify all these things that I am just simply going on writing, and see that all of them are correct. If you ever come across some mistake or something, please let me know. Okay, so let's just leave it like this. So this is the permutation representation of our S3, the symmetric group of degree 3. Now let's see the next one. In the next one, we will come across a group which we so far haven't seen. I mean, in this book, it's a non-abelian group of order 8, and it has a name also. Its elements are called quaternion units. If you already know about real quaternions from ring theory, then you know about this group. So this is the next one. Exercise 21. Let G be the group E theta A B C theta A theta B theta C, where some relations are satisfied by these symbols, and those relations are these. The squares of A, B and C are all equal to theta. The square of theta is equal to E. E will be the identity, you can understand, and AB equal to theta BA is equal to C. BC is equal to theta CB, that is equal to A, and CA is equal to theta AC is equal to B. But still, let me see if I am correct or not, or have I made a mistake. AB theta BA is C, BC theta CB and CN. Okay. Okay, now there are some parts. We are being asked to not only find the permutation representation of this group, but some other things also. So the first one is this: show that theta is in the center set of G. If you are following American English, then of course this is CE and TER, and it's not Z, it's Z. And that in fact this center it consists of the element E and theta. That's what we have to show. Next, part B. In part B, we have to find the commutator subgroup of G, that is the derived subgroup of G. Part C. Show that this is a very important property of this group. Show that every subgroup of G is normal. And then finally in part D we will be asked for the permutation representation. Find okay, and there is a note also which says that G is often called, I am not writing the note here because I ran out of space. G is often called the group of quaternion units because if you are familiar with the ring of real quaternions, there is a ring structure whose elements are called real quaternions, whose elements look like this: A plus Bi plus Cj plus Dk, something like that. In that ring, the unit elements form a group. It is this group. Okay, so it is called the group of quaternion units, and the author writes, it and algebraic systems constructed from it will reappear in this book. Okay, so let us now start the solution, but before we start the solution though, I want to draw your attention to something about which I already discussed before, I think several times. You see that sometimes, most of the times in this book and elsewhere, groups are presented like this. A set of some symbols is given and then it is said that some relations are to be satisfied by these symbols. Now there is something in group theory called presentation of groups, which itself is a theory. It tells us that if such a set of symbols is given and some such relations are given, roughly I am saying, okay, then groups exist. That means binary operations exist, which if you impose on that set of symbols, then the relations will be satisfied and the system will be a group. However, we do not know presentation of groups, and also in this book it's not mentioned. So for us, it's just a statement that actually needs to be verified. Although the author is casually writing let G be the group in which these things happen, what we really should do for our own sake, if we are really serious and we want to know really about these things, what we should do is that we should actually introduce a binary operation on this set of symbols that will first of all turn it into a group. That is the first thing, and such that in that group these relations are true. I have done it before also in some other exercises where Herstein presented some groups like this. I tried, in fact I successfully defined some binary operations in those cases which turned the system into a group and where the given relations are satisfied. Here also I am going to do that. Okay. So what are the parts? Now before I erase things, we have to show that in part A we have to show that this is the center. Okay, center consists of E and theta, and then we have to find the commutator subgroup of G. We also have to show that all the subgroups are normal, and then finally we have to find the permutation representation. So let's start. Because we have the relations here, let me erase this part itself. Now since the group is not an infinite group, it's the set is a finite set. So the best way to define a binary operation is by constructing a composition table, a group table, and that table we are now going to do, and that's the first thing we are going to write in the solution. The following table defines a binary operation on G. The author is mentioning, is simply stating that G is a group, but for us G still is just simply a set. It's after we manage to show that it's a group, it will be a group. It is, but for us not yet. So there are 8 symbols, so I will need 9 rows and 9 columns. Just bear with me, it won't take long. One, two, three, 4. I think I will need that part also fully. So why not join these things? Okay, it will be a little tight, but still I'll try to make it as clean as possible. But once we finish drawing the cells, then inside the cells, when we put the entries, we cannot afford to make any mistake, because then it will be very difficult to erase things cleanly and then rewrite them. I hope I haven't messed up the counting. One, two, three, four, five, six, seven, eight, nine. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So let's start writing the elements. E theta A B C, theta A, theta B, theta C. Okay, so let me now copy this thing carefully. The rows and columns corresponding to E are easy to fill out because we want E to be the identity, so nothing will change. Next. Okay, let me just simply blindly E theta A, theta B, theta C, and then ABC. Theta B, theta C, A, B, C. Okay, next, the row of A. Theta A, theta C. Theta A, theta C. Theta B, E, theta C, B. Theta B, E, theta C, B. Then the row of B. B, theta B, theta C, theta. Theta B, theta C, theta. Okay. B, theta B, theta C, theta. Then ACE, theta A. Okay. Then the row of C. C, theta C. B, theta A. Theta. Theta B, AE. Then the row of theta A. Theta A, E theta C, then B theta C, theta B, then the row of theta B. BCE, BCE. Yeah, there is a chance of getting confused between C and E. This is E, but this is, I will explain some things about this table. Let me first write things down. Theta B, BCE, theta B, BCE, theta A, theta C, theta A. Theta A, theta C, theta A. And finally the last one. C, theta B, AEB, theta A, theta. Okay, so this awful looking table is actually the one that defines a binary operation on G, and it's a binary operation, there is no doubt about it. That's because all the entries are again in G, but the daunting task is to verify that this operation is an associative operation. Now, believe me or not, I have gone through the pains of actually writing down all the possible products of 3 elements and verifying that yes, this is an associative operation, which of course I am not going to do here. It's left to you. Either you can take my words for it, or you are, in fact, you should go through that same process of verifying that all the products in fact are, it's associative, the operation is associative. All the possible products, no matter how you bracket them, give you the same element. So it's associative. Let's just assume that. Now next comes the question of existence of identity, which we can see from the table clearly that E acts as an identity. You take any group element G, EG is G, that you can see from the first row, and also GE is also G, that you can see from the first column, means this column, first row means this row. And what about inverses? The inverse of E is E itself. The inverse of theta is theta itself, because theta is E. And A and theta A are inverses of each other, because you can see A, theta A is E. Also, theta A is E. Similarly, B and theta B are inverses of each other, and C and theta C are inverses of each other. So it is a group. And one more thing is that it's a non-abelian group. Why? Because AB and BA are not the same. Oh, but before I use these things, you can use the table and see that all these relations are true. Let's just see a couple of them. What about the squares of A, B and C? A square is theta, see? B square is theta, C square is also theta. And what about theta square? Theta is E. Fine. What is AB? ABC. What is theta BA? This you can interpret as theta B times A, say. Theta B, in the row of theta B, you look at the column of A, C. Similarly, the other relations are also true. Okay, now we come back to the question of the group being non-abelian. It is non-abelian because AB is C, whereas what is BA? BA is not given here, but it will be given here. BA is theta C, and C and theta C are not the same element, they are different elements. So it's a non-abelian group of order 8. Now if you want to answer part A, you have to show that the center has only these 2 elements. Out of these 2, E is always there, of course, and theta is also there. Do you see why? Because theta commutes with every element. A quick way to verify that from a table like this is to see that the row corresponding to theta and the column corresponding to theta consist of the same elements in the same order: theta E, theta A, theta B, theta C, ABC. Theta E, theta A, theta B, theta C, ABC. So that's why theta commutes with everything. But also you have to make sure that none of the other elements commutes with everything. For example, you can take A. Already we have seen that A does not commute with B, so A cannot be a central element, and because of that B is also not a central element because B does not commute with A. Similarly, this one shows that C does not commute with B, so C is also not a central element. Similarly, you can show that these other elements theta A, theta B, theta C, none of them is a central element. So the center consists of this. So let us now write all these things. So what I am going to do, I will keep the table of course, but I am going to keep the relations also. For now at least. So let me continue my solution from here next. One can verify that G is a group under the operation defined by the above table. Do I really need to keep this part because we have already seen that they are satisfied? So that means I have more space. Defined by the above table, in which this also needs to be mentioned, the given relations, that is these relations hold. Okay, now we start answering the actual parts, that is parts A, B, C and D. Mostly it's just a matter of writing the thing again. That is just simply whatever is being asked in the question, you just write that itself because it can be verified from the table. Which please do, actually do verify. Do not just simply write down for your own sake. One can see from the above table that the center is what is being claimed. Okay, so that is part A, and it's not a very computationally heavy task or anything. Just like how I described how one can show that the center is this, you can show. Now we are going to answer parts B and C together, and we are going to answer part C first by actually writing down all the subgroups of G. The subgroups of G are the trivial group of course, and then our center, and then there are 3 subgroups each of order 4. EA although it does not matter which element we write first, but still E theta A, this is a 4 order subgroup. Just like that, E theta B is another one, E theta C is another one, and then there is of course G itself. Now, how do you make sure that these are the only subgroups? You just have to somehow argue, but before that, are these subgroups really? There is no doubt about E, Z and G. What about these other three? For any one of them, you just have to show that because we are dealing with finite sets, that for example this set is closed under the formation of our product, which you can verify. Okay, so just like that, these remaining three are also subgroups. Now we have to answer part C, right? And what about that thing that these are the only subgroups? That you can take the help of Lagrange's theorem for this. What does Lagrange's theorem say? It says that because G is a group of order 8, any subgroup should have order which is a divisor of 8. Now the divisors of 8 are positive divisors 1, 2, 4 and 8, and we have in fact found subgroups for each possible order. Now in finding subgroups of a given order, there you have to just somehow manage this task. Okay, somehow, in fact this is left to you to show that besides these subgroups there is nothing else. Okay, I am leaving that entirely to you. Somehow you prove that there is no other subgroup. Okay, now the thing that we need to next show is that all these subgroups are normal, because that's what C asks. The subgroups E, Z or Z and G are of course normal, because these two are normal in any group, and this is normal because this is the center is in any group, the center is the normal subgroup. The remaining subgroups are I was going to do something very bad just now. I was going to do this. Okay, we would have lost everything. The remaining subgroups are normal because each one of them is of index 2 in G. G is an 8 order group and these are 4 order subgroups, so each one of them has index 2, and we have already seen previously in one exercise that any index 2 subgroup is normal. Okay, but how do we answer part B? So we have in fact shown that all the subgroups are normal. Now in part B we are asked to find the commutator subgroup. Okay, now for that you consider the quotient of G by any one of these 4 order subgroups. you can consider the quotient because now they have been proved normal. Now, since the this quotient group say is abelian. Why? Because it has order 2. So by a previous exercise, whenever you get a normal subgroup in a group for which the quotient, if you form it turns out to be abelian, then that normal subgroup contains the commutator subgroup. We have got this previously in one exercise. I don't remember which one exactly, but you go to the section on homomorphisms, I think it is there, exercise 5 or something. So because of this, the commutator subgroup is contained in this. Similarly, we could have done this for the other two also. G prime is contained in and G prime is also contained in the third one. That means G prime is contained in their intersection. Now the only common elements to all these three are E and theta. So G prime is contained in this subset which actually is the center, but also we have this fact: theta is equal to AB, theta A, theta B. Is it really the case? Let's see the table. What is AB? AB is C. AB is C. So that means this is C. What is theta A, theta B? Theta A, theta B is C. So that means C and C. C square is CC theta. Yes. And we have already, which also we can see from the table, that theta A is the inverse of A, theta B is the inverse of B. So that means this is AB, A inverse, B inverse, which is a commutator. So it should belong to the commutator subgroup. Now we already know that because the commutator subgroup is a group, E belongs to this and now theta also belongs to this. So this is also a subset of this, and that's how they are equal. So hence the commutator subgroup is actually equal to the center itself. In one of the previous exercises, we used this group. That time we only mentioned it, but now we are dealing with it. Hence, this. That exercise, asks us first of all to show that in an abelian group, every subgroup is normal, which is almost trivial, so we did that. And then the exercise asks us to show that the converse is false. So this is a counter example to the converse. This is a non-abelian group, but in it all the subgroups are normal. And now finally we come to part D, which is about permutation representation. D. In A of G, because G has 8 elements, so its permutation group is isomorphic to S8. In it, now we have this again, those tau functions. So the beginning is trivial, tau v is E. Then next, we have to write many, eight of them. Na? E comma theta, A comma theta A, B comma theta B, C comma theta C. So that is tau theta. Next, tau A. Tau A is E A theta theta A. And B theta C, theta B C. Next, tau B. Tau B is E B theta theta B. E B theta theta B. Then A C theta A theta C. Do you notice one thing, that if you really think about it, the numbers, ordinary numbers that we are extremely familiar with, that is 1, 2, 3, these integers, actually they are also abstract symbols only, no? But because of our familiarity and because we have been working with them for so long, that we are so comfortable that we, anytime a calculation or something appears that we need to do, we just readily start doing everything. But when we encounter objects like this, which are also abstract symbols, satisfying some properties, doing some things, every time we try to take a step, we have to think twice, 3 times, 100 times. Is it correct? Now, if you are given enough time and for some reason you have to use these things again and again, then you will get that fluency even with these symbols. I think that is why it is sometimes said that we need to practice math. E C theta theta C. A theta B theta A B. Then tau theta A. Okay, this one is E theta A theta A. Then B C theta B theta C. not only should we get the symbols correct, but we should get the orders also correct. Any slight mistake is just simply it will make the whole thing wrong. E theta B theta B A theta C theta A C. And finally tau theta C is E theta C theta C A B theta A theta B. Would you like to verify at least one? Let's verify tau theta A. Okay, so that means we are multiplying every group element from the right side by theta A. We multiply E by theta A. E theta A is theta A, so E goes to theta A. Next, theta A, that means theta A square. Theta A is theta, so we have theta. Theta A is theta square A, but theta square is E, so we get A. And then A theta A, because A and theta A are inverses to each other, so that becomes E. So this part is okay. Then what about B theta A? Let's see the table. B theta A. B theta A is C, so B goes to C. C theta A is theta B. Then theta A. Theta A is theta C. And finally theta A is B. So this goes back to B. So like that you can verify that the others are also true. So that's how we have all these things. So let's just write the final line. With this, the permutation representation of G is our function psi. Here we don't have any psi already. Okay, from G into A of G, which is isomorphic to S8, and of course our psi has this definition, and that is the solution. There is one more exercise after this, which of course we are not going to do tonight, which asks us to find the permutation representation of a dihedral group. Now there the task becomes even more challenging computationally. That's because here itself you can see that okay, it's straightforward, but you have to do a lot. There, however, the problem is that a dihedral group is also finite. Okay, I mean the one we have got is finite, but the number is a general number, 2n. So we will see that in the next video. And there is another type of representation, second permutation representation, where instead of using the taus we use lambda. We will see what this, and then after that we have coset representations also. So these things will come, which we will see in the next group theory video on Herstein. And the next upload is this coming Friday. And what shall we do? Let's do field theory. So with that I wrap things up for tonight with this awful looking table. So see you on Friday with field theory. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.